Hello there once again. Welcome back to our Chem 152 video series. In this video, we'll be doing a problem regarding osmotic pressure. This question says that we have a 5% by mass aqueous solution of Na2CO3. We're given the density, we're given a temperature of 25 degrees Celsius, and we are asked for the osmotic pressure. The osmotic pressure is equal to I times molarity times R times T. The P stands for osmotic pressure, and in this problem we'll be doing the osmotic pressure in atmospheres, or ATM. The I is the Van't Hoff factor. Think of this as the number of ions that are in the solute. Capital M stands for molarity. This is our moles divided by liters, specifically moles of solute divided by liters of solution. The R is the gas constant. You have two options for the gas constant. The one we'll be using in this problem is 0.0821 atmosphere liters over mole Kelvin. You may have seen another version of this that goes 8.314 joules per mole Kelvin. You'll be using this if you're trying to go for pascals for your pressure. However, for this problem, we've specified atmospheres, so we'll be using 0.0821 because that has atmospheres here on the top. Now the T stands for temperature, but this temperature must be in Kelvin only. It cannot be in Celsius. Now that we have the equation and we know what the symbols mean, let's see how many of these symbols we know before we continue. Now, if we have a look at line 2 says, what is the osmotic pressure? Meaning that's our ultimate goal for this problem. We'll box that in red to show that's what we're trying to get at the very end. Now we look on the right side of the equation. Let's look at the Van't Hoff factor first and examine the solute. Our solute is Na2CO3. Now Na2CO3, if you've taken Chem 151 here, you'll know that is a soluble compound. It is a strong electrolyte and it will break into two pieces of Na positive and one piece of CO32 negative. Recall that CO32 negative is a polyatomic ion. It will not break down any further, and it will just stay as CO32 negative. The two pieces of sodium will also break away from that. This gives us an I of 2 for the sodium plus 1 for the CO3, gives a total of 3 ions, meaning our Van't Hoff factor is 3. We'll check that off to show that we know it. Now, our molarity is not given anywhere in this problem. We have a mass percent, but that's not the same as molarity. So I'll put a question mark next to molarity. We're going to make a note that we're going to get this from the mass percent. We have enough information to get molarity, but let's finish collecting the rest of our information before we try to do that. The next letter in the chain is R, the gas constant. Because we are told that the osmotic pressure is going to be in atmospheres for this problem, we'll use the atmospheres version of the gas constant. And we'll have 0.0821 atmosphere liters per mole Kelvin. That will be a known number, and we can check that off. Our temperature will be 25 degrees Celsius, but we cannot use Celsius in this problem. We must change to Kelvin. And to change to Kelvin, we add 273.15 and get a total of 298.15 Kelvin. Therefore, we know the temperature, and we can check that off as well. If we look on the right side of the equation, the only thing we don't know is molarity. And so our first step is going to be to get molarity. After we get the molarity, we'll have as many letters as we need to get the pressure. Let's remind ourselves once again that molarity is moles of solute divided by liters of solution. In line 1, we are given that we have a 5% by mass aqueous Na2CO3 solution. So we're dealing with mass percent here, which means we can start with a basis of 100 grams of solution. Of those 100 grams of solution, 5 of those grams will be Na2CO3. So part A of this process will be to get the moles of solute, and part B of this process will be to get the liters of solution. For part A, we'll start with our grams of solute, which is Na2CO3, and go to moles of solute. We'll start with our 5 grams of Na2CO3. We'll get out of grams and get into moles. We'll write that we have 2 NAs, 1 carbon, and 3 oxygen. So for Na, we'll say 2 times the molar mass of Na. On your periodic table, that would be 22.99, giving us 45.98. For carbon, we'll have 1 times 12.01. And 3 times oxygen is going to be 3 times 16.00 for a total of 48.00. Add all of these numbers together to get the molar mass. We'll get a total of 105.99. This will go next to grams. With a 1 next to moles, now we divide 5 over 105.99. We will get 0.0472 moles for our Na2CO3. That's our answer to part A. For part B, to get the liters of solution, we'll start with our grams of solution. We cannot go straight to liters. We have to stop in the middle at milliliters and then go to liters for a 2-step conversion. Our grams of solution were 100. We'll multiply by a fraction to get out of grams and into milliliters. Our density is 1.05 grams per ml, so we'll say 1.05 on the bottom, 1 on top. Multiply by another fraction to get out of milliliters and into liters. 1 liter is the same as 1,000 milliliters, and so we'll do the operation 100 divide by 1.05 divide by 1,000. We'll get 0.0952 liters. And so to get molarity, we'll place our moles on the top and our liters on the bottom. We'll divide 0.0472 over 0.0952 in the calculator. And we will get 0.4956 molarity. Now that we have the molarity, let's have one last look at our equation. Now that we've found the molarity, we'll say that our pressure is equal to I, which is 3, times the molarity, which is 0.4956, times the R, which is 0.0821, times the temperature, which is 298.15. Multiply all of those together in the calculator. When we multiply, we end up with 36.4 atmospheres. This will be our osmotic pressure for the solution. Thank you for watching. We'll see you again soon.